So the other day we were talking about acceleration, and we went over 4 different acceleration formulas. We went over the one from Science 10, okay, that was change in velocity over change in time. Okay, we went over the D equals VF plus VI over 2 times T formula. We went over the 2 that calculate the area under the line on the velocity versus time graph at VI times T plus 1/2 AT squared, VFT minus 1/2 AT squared. We went over those. We still have 1 left to go over. Okay, so that's what we're going to do today, and then we're going to kind of practice figuring out which formula to use and how to manipulate them and all of that kind of stuff. Okay, we're not going to spend a lot of time on doing that because it's basically just algebra. Okay, and at this point I expect you guys know how to manipulate an equation to solve for something. So we're not going to spend a lot of time on it because we need to get to projectile motion soon. Okay, projectile motion is the last thing in this unit, okay, and it basically combines everything from this unit except graphing, right? So there's some v equals d over t, there's some vector components, and there's acceleration in it. I know that makes it sound hard, but it actually isn't. They're all quite separate procedures within it. We just have to do them all in one question, okay? So that's what we'll be looking at, but obviously we have to have gone over acceleration before we can do that. So I would like you to write down this example here. Okay, because this will be our example for our final formula. Okay, it's a little violent, but it's the one we're going to do. Okay, so we have a bullet that is accelerating through the length of the barrel of a gun. Okay, now, in case you don't know how a gun works, okay, when you pull the trigger, a little hammer comes forward and strikes the round. Okay, inside the round is where the gunpowder is. Okay, the gunpowder is detonated; it explodes. Okay? An explosion produces expanding gases, and those expanding gases are trapped within the barrel of the gun. And as a result, they push the bullet forwards as they expand. Okay? And the longer the barrel, the longer they can exert that force over, and the faster the bullet will go. Okay? Also depending on how much powder there is, obviously. Okay? But they basically push on the bullet as long as it's in the barrel. Once the bullet exits the barrel, then the gases aren't contained anymore, they don't exert any pressure, and the bullet is no longer speeding up. Okay? Now, how fast can a bullet go? Very fast. Okay? If you had a very high-powered rifle, okay, you could shoot a bullet at 3 times the speed of sound. Now, here's a thought you can rock yourself to sleep tonight with me. Think about that. The bullet is going faster than the sound of it being shot. What does that mean if you're the target? Right. You would not hear the bullet. You would not hear the shot. Okay, that's a little scary. Okay, but it's true. Okay, whenever they show, like in movies, recent movies, they actually do a pretty good job of showing that. Like if you've seen American Sniper and things like that, they actually do a pretty good job of showing that stuff. But lots of movies don't, and you see these people and then they're like bobbing and weaving and ducking because they hear these shots being taken that you wouldn't hear the bullet. It would be just, that's it. Okay, and oftentimes when they show footage, real footage of snipers taking shots at targets, at people, unfortunately, if they miss, the people do not look in the direction of the shot. They look at the ground where the bullet hits, because that's what they hear. They hear the bullet striking the ground. So they look down, they see this puff of dirt, okay, and then you see their head go like this, because then they hear the shot, okay, and then it's usually bad news for them. It's usually a person of that caliber doesn't miss twice. That was a pun, by the way, caliber. That's a dad joke. Fun. Okay, now, here's another scary thought for you. The longest kill shot is held by a Canadian. Canadian sniper owns the longest kill shot at almost 4 kilometers. That's scary. Okay? You can't even see something 4 kilometers away. Okay? Like that's like if you looked out this window, okay, that's like way out there. Okay? 4 kilometers away. Now, that's not just a case of, I'm really good, I just pick up my rifle, look in the scope, and pull the trigger kind of a shot, okay? A sniper of that ability, that caliber, okay? A sniper of that caliber is going to have to do a lot of like calibrating, calculating, okay, things like that. That's usually why they work in pairs. They have a spotter. If you've seen American Sniper, he always has a spotter with him. Okay? The spotter is telling him things like range, elevation, windage, okay? All of these things that can affect the flight of the bullet on its way to target. Okay? One of the things they have to take into account is when they shoot, the bullet is affected by gravity. And over its entire flight, it's always falling. So if you're taking a shot at something 4 kilometers away, it's going to be in the air for 3 to 4 seconds, maybe longer. It's going to fall a long way. They would be aiming several meters above their target. So like the barrel of the gun would not even be, yes, it would look like that. Okay? If I'm pointing at if I want to shoot that over there, I have to point my gun up in the air. Okay? So the bullet will arc down towards the target. Okay? And that's just the elevation difference. Then you've got windage. Okay? Any wind blowing across the shot could push the bullet one way or the other several feet, okay, throughout the flight of the bullet. That has to be accounted for. And for a shot of that length, the earth will rotate under the bullet while it is flying. And that has to be accounted for because it's in the air for so long. Okay? Any shot where the bullet will be in the air for more than 1 second, you have to take the Coriolis effect into account. Okay? It is crazy that somebody could actually make a shot like that, and a little scary. So that's not a guy you want on your bad side. Okay? Because you'll never know it. All right. Now that you have that pleasant thought, let's look at this question. So first thing I want to do is write down my givens. Okay? We have the distance over which the bullet accelerates. That's the length of the barrel. Okay? So 0.750 meters, okay, is the distance over which the expanding gases are pushing on the bullet. Okay? The acceleration of the bullet is massive. 5.35 times 10 to the 5 meters per second squared. Okay? That is a massive acceleration. And what speed is the bullet going before you pull the trigger? 0. We have to assume that, okay, in this case. It would be really hard to shoot a bullet that was already moving. Although apparently there's one in a museum where there's like 2 bullets that are like merged like this, where they actually hit each other flying through the air. 1 in a million, or 10 million, something. Okay, so we've got D, A, VI, and they want us to find out what speed the bullet exits the barrel. So that would be VF. All right, so we've got those 4 things. Okay, that means we're using the last formula. VF squared equals VI squared plus 2 times A times D. Okay, and in this one, we don't have to manipulate because it's asking us to solve for VF. Actually, we do have to manipulate. What do I have to do? I have to square root because this formula solves for VF squared, and I just want VF. Right? So I'm going to have VF equals the square root of 0 squared plus 2 times 5.35 times 10 to the 5 times 0.750. Okay, so we've got the square root of, I'm not going to put the 0 in because in this case mathematically it doesn't matter. Okay, 2 times 5.35 times 10 to the power of 5 times 0.750. All right. The bullet leaves the barrel of the gun at 896 meters per second. The sound of the shot will travel at 340 meters per second. Okay? Which means every second it's in flight, it's getting 556 meters ahead of the sound it produces. Okay? So yeah, by the time it gets to target, it's pretty far ahead of the sound. All right, now, again, that's for a rifle. A pistol would be considerably different. Okay, a pistol would obviously not fire a bullet nearly as fast, okay, because it doesn't have as much powder in the cartridge or the length of the barrel over which to accelerate the bullet. Okay, so a pistol fires, or a handgun of any kind fires bullets at a much slower rate. Okay, that doesn't make them any less deadly. At close range, it doesn't matter. Okay, long range, okay, it makes a difference then. All right, now let's have a look at some manipulations of that formula. So our initial formula was VF squared equals VI squared plus 2 times A times D. All right, so if I wanted to manipulate for VI, what would I do? Right, subtract 2AD. So I'd have VF squared minus 2 times A times D equals, equals VI. But what would I have to do to it? Square root, right? Okay, that would equal VI. So that's a fairly simple manipulation right there. Okay, what if I wanted to solve for A? What should I move first? Yeah, move the VI. Okay, so VF squared minus VI squared. Okay, and then divide by 2D. That would leave me with A. If I wanted to solve for D, I'd divide by 2A. All right, it's actually a pretty simple formula to manipulate. All right, so I want you guys to try these two. Now, the first one actually doesn't require you to use the new formula. Okay? For part A, you have to pick which formula you're going to use, and for part B, you can use almost any formula you want. Okay? Question number 2 requires you to use the new formula. All right, get to work. So this is the challenge with acceleration problems, is I get a question, I have to read it through, decide what I'm given, and then figure out what formula I have to use to solve that. Okay, so in question number 1, we have a jetliner that lands on a runway at 70 meters per second. So VI is 70 meters per second, and then it comes to a halt. So VF is 0. Okay, and it does that over 29 seconds. Right, so we're looking for part A for the acceleration. All right, what formula do I have that can use those 3 things to get acceleration? Right, A equals change in velocity over change in time. Okay, so that's going to be A equals VF minus VI over T. Okay, so we just plug in our numbers here. That'll be 0 minus 70 over 29 seconds. And so that should give us our negative 2.4 meters per second squared. I don't know why anyone would write negative forward. That's just dumb, backward. Okay, or just negative would be fine. Don't write negative forward. That's like saying negative right is wrong. It's true, but it's not. No one says it that way. Okay. All right. Then for part B, it says, what length of runway did the jet require to come safely to a complete stop? I've got VI, VF, T, and A. Now, I can use any formula I want now. Okay? Any one of the formulas will work. Okay? I would say probably the quickest one, and it wouldn't require any manipulation, would be to use this one. D equals VF times T minus 1/2 AT squared. Okay? Because what's VF? 0. Right? So for this one here, I just plug in my numbers and go 0 minus 1/2 times negative 2.4 times 29 squared, and I'll get 1 kilometer for my answer. I could use any formula I want. I could have used VI times T plus 1/2 AT squared. I'd get the same number. Okay. I could have used our new one, but I'd had to manipulate it. Okay. That was quicker. Everybody okay with that? Okay. How many people have done number 2? All right, I'm going to give you a couple more minutes on number 2, and then we'll walk through that one. All right, so question number 2, okay, talks about how on-ramps are designed. So they have like a freeway interchange, like the cloverleaf, if it's properly designed, okay, is going to have the merging lane, okay, the on-ramp that you come down and get onto the highway on. Okay, when a city planner or architect is designing that, they need to know how long it needs to be. And to do that, they need to know what speed the cars will come onto the ramp at, what speed they need to reach by the time they're at the bottom of the ramp and merging, and the average acceleration of vehicles that will use the ramp. Okay? You don't want to design this ramp for the highest performance sports car ever built. It'll be too short for everybody. Okay? On the same note, you can't really design it for the slowest vehicle either, otherwise you're wasting resources. Okay, you're going to build this incredibly long ramp and people are going to be driving on it for 2 kilometers. It doesn't need to be that long. Okay, yes, maybe your semi-trucks will struggle a little bit if they're fully loaded, but in general you kind of go with a low average, okay, to design the ramp with. Right? Now that's for a properly designed interchange. Obviously in Calgary, lots that are not. Okay, they all have stoplights at the top, so VI is usually 0. Okay, for all of those, and then they're not long enough where people don't know how to merge and they go really slow. You know what I'm talking about, right? That person you get stuck behind when you're trying to get out on the highway 2 here and then merge like they're in a walker. Yeah, it annoys the heck out of me. Merging means get up to speed right away. Rant over. Okay, so what we have here is an initial velocity of 50 kilometers per hour. So VI is going to be, we have to divide that by 3.6 to get it in meters per second. So that's going to be 13.8 repeating, okay, meters per second. VF is 100 kilometers an hour. That's 27.7 repeating meters per second. And we know the average acceleration of the vehicles is 3.8 meters per second squared. All right, so that's the information we have. We're trying to find out how long the ramp needs to be. Okay, so we've got VF squared equals VI squared plus 2 times A times D. That formula has our givens as well as what we're looking for. So I need to manipulate it for D. So I'm going to subtract VI squared over and then divide by 2A, and that will leave me with D. Okay, when I plug in my numbers, that's going to be 27.7 squared, okay, plus 13, sorry, not plus, minus 13.8 repeating squared, okay, divided by 2 times 3.8. Okay, so when we punch that in, okay, we're going to have 27 bunch of 7s squared, okay, minus 13 point, a bunch of 8s squared, okay, and then divide that by 2 times 3.8. All right, so we're looking at an on-ramp that's going to be 76 meters long. And that will allow cars to get up to speed before they have to merge. All right, everybody okay with the use of that formula? Okay, so like I say, the importance of acceleration is obviously you'll probably have an acceleration problem on your unit exam, but it's also going to be part of projectile motion. And it's the same idea. You're going to have to figure out which acceleration formula to use for the accelerated motion part of projectile motion, and that's the vertical part. Okay, because any projectile flying through the air is obviously being pulled down towards the ground at 9.81 meters per second squared. Incidentally, that is a number you kind of need to have in your head. Yes, it's on your formula sheet, but lots of times a question will seem like it doesn't give you enough information, like it doesn't give you enough numbers. Then you have to go back and look at the context of it. Did it say something like an object was thrown up into the air or thrown downwards or something like that? Anytime something is moving vertically, its acceleration will be 9.81. So you kind of have to look at the context of the question to see whether your acceleration is gravity or not. All right, so on that note, I would like you guys to be working on, okay, these acceleration problems here. They're in your digital workbook starting on page 6. Okay, if you want to have it on your phone instead, but I'll put these ones up here. Question number 2 is an example of what we just talked about. Okay, if you drop something, it's going to accelerate at 9.81. Incidentally, if you drop something, what's its initial velocity? 0. Yeah. Okay. So things like that are contextual things. They don't outright tell you a number, but they kind of do. All right, so let's get to work on those, and then I'll go through any that give us trouble. If you're needing some help, just put your hand up, and I'll come around and help you. Okay, so looking at number 4 here, guys. I have a proton that's accelerated in a linear accelerator. So this would be like the Large Hadron Collider that they use to make the Higgs boson thing. Okay, so it's accelerated in this accelerator. The accelerator is 800 meters long. So the distance over which it is being accelerated is 800 meters. Okay, how long does it take? So we're looking for time to get from rest to 2.5 times 10 to the 8 meters per second. Now that's incredibly fast. Okay, that's relativistically, like it's a relativistic speed, which means it's close to the speed of light. right? So like time would slow down, all that kind of cool relativity stuff. Okay, so we're looking at calculating the time for that one. So I would use this formula: D equals VF plus VI over 2 times T. All right, I have VI, I have VF, I have D, I just don't have T. But I don't have acceleration, so I can't use any of the other 4. They all have A in it. Okay, so I'm going to divide the brackets over to the other side. Okay, and that will equal T. All right, so I just plug in my numbers now. So that'll be 800 meters, okay, divided by 2.5 times 10 to the 8 plus 0 over 2. Okay, so when we do that, okay, we're going to get an incredibly small time. We're going to get 6.4 times 10 to the minus 6 seconds. Because when you're moving that fast, does it take very long to go 800 meters? I mean, you don't notice a delay when somebody turns on a flashlight, okay, you know, over there. Or someone turns on a light in that condo complex. The light gets here like pretty much immediately. It doesn't take very long for something going that fast to go 800 meters. So we're going to get an incredibly small time. Okay, any other ones?
Oh, I just had a question about that one.
Okay, question?
So the power of -9 is the power of -6.
Because, did you convert this to meters? That's right. That's your 10 to the 3 right there. Okay, any other ones, guys, that we need to go over? Okay, keep going then.